Let's work out the truth table for a 3-input AND gate, which we see the logic circuit for right here, and has an equivalent symbol right there. So this is a pretty common symbol to see. 3-input AND gate, we see it represented by like this. These two things are equivalent. In a circuit, you may find two AND gates put together in combination that are represented by this 3-input AND gate. They are the same thing. Essentially, they output the same thing. And let's look at how that happens. Remember, whenever I have a complex circuit like this, multiple gates, I like to break it up in chunks. The smaller chunks are easier to deal with, like this one. We see that it has two AND gates. There's an AND gate there and an AND gate there. So something is coming out of this AND gate, and whatever comes out of there is going to be the input into this AND gate. So we want to evaluate that, and we want to figure out what this output is that's going into the other one. And to make this easy, we're going to call that W. Whenever I have complex or multiple gates combined together, and I do that, I separate these gates out. I write an additional variable in there so that we can keep track of that. I got to make my truth table large enough with enough columns to represent these variables that we're adding in. Okay, so I've got a W. That's going to be the output of this AND gate, of A and B going into this AND gate. So we're going to be evaluating A and B, and outputting it here at W. So you see here, first I've got a 0 and a 0, and we know the rule for an AND gate. It's only going to output a 1 if A and B are 1. So looking at these, I've got a 0, a 0, a 0, and here we are. Got a 0 and a 1, a 0, a 0, a 0, and finally I've got a 1 and a 1, so I can output a 1. And the same thing there, there's a 1 and a 1, so we can output a 1. Now that we've evaluated this AND gate, and it's resulted in W, which we have here, we can evaluate this AND gate, because it's got W going in as an input, and C going in. So whatever the output of this AND gate is, it's going to be our output of the circuit. Well, W and C have to be 1 for us to get a 1 as the output. So W and C are what we're evaluating. We have to get a 1 and a 1 to output a 1. We don't get it there. Don't get it there. The only spot that we get a 1 and a 1 finally is right there. So remember, these two things are equivalent. This circuit and this one. We may see this one written out from time to time, but know the rule. We proved it with these two gates. We separated it out. We looked at the combination of the gates, and to get an output of 1, we have to have A, B, and C being 1 on this 3-input AND gate to output a 1. There's my Boolean expression for a 3-input gate. And remember, an AND is using the multiplication symbol, so I've got an A and a B ANDed together, and then the combination of that is ANDed with C. Oh, and look here, I've got an A and a B ANDed together, which is ANDed with a C. A and a B together ANDed with a C, and that's my output. So really Q would be more appropriately represented by this Boolean expression right here. A and B ANDed with C. It would be good to note that also this is equivalent with the associative law would tell us that this is an equivalent Boolean expression to this. This and this are the same thing. The associative law says that we can AND things in any order like that. And there's our completed truth table. Our Boolean expressions are shown all here in their equivalent spots. It's more appropriate to show our output as this Boolean expression rather than that unknown variable, which we're using Q as a placeholder.